think the committee members, they have the costume.
What do you dress up?
I dress up in the store.
Oh, okay.
Yeah.
Nice, man.
But Hamill go to the same store as me. So when I leave, then he just comes. Yeah. So they do that. Hello. Hello, guys. Really, thank you for being here with me. Yeah, it's really my honor to have all of you, and all the my family members, friends, colleagues, online behind the screen. I really appreciate your support. So now I will start a 15 minutes talk on my defending topic. It would be alluvial stratigraphic response to astronomical climate forcing. So the presentation will be mainly including 4 parts. So first, I will introduce a bit to you on what I'm working on. Then I show you some results of the numerical modeling, and also the outcrop analysis. Then in the last, I show you some photos of our fieldwork. Yeah, basically the funny part, one example day of me as a field geologist. Yeah, so let's first look at some animations. We all know that the Earth is spinning around the sun with some orbital parameters. Yeah, like here you see, oh sorry. Yeah, like here you see, so the axis is in the motion or precession, also including so like a spinning top. Also, the orbit is also in the motion or precession, so they all make slow motion that change. Then we have the obliquity of the Earth's axis. They are changing gradually in time. Then the Earth's orbit is also moving from a circle to an eclipse, back and forth. So all these parameters influence the insolation received on the top of the atmosphere, then they will cause climate change. This climate change will be felt by the rivers, by the lakes, by the other landforms. Yes. So now all this change can be kind of quantified using those curves over the last 1 million years, but we cannot go back too far in the geological past due to our poor control. Yeah, so there has been lots of success in the cyclostratigraphy in the marine and the cartographic domains. So here you can see there are some beds. Yeah, so yeah, sometimes they are in bundles, sometimes they are very regular. So they are all the results of the orbital forcing, but it's quite challenging in the river part. Why? Yeah, because here you can see, so there's a nice animation showing how the settler effect works. So there are many events. They are mostly erosive. So you can see they are not preserved in the stratigraphy. So our stratigraphy record is more gaps than the than record. So it's quite challenging. So now, so here is a nice diagram showing everything moving from the catchment and then to the sink. Oh, sorry, catchment to the sink. So it's similar to a tube, like you have some sediment input on the upper left, like here, but sometimes, so you have some very nice, like cyclic inputs. But then there's some bad guy that's very powerful, so it shredded everything, then eventually you get your signal shredded. But in some other cases, you have, so your signal is too strong, then these guys are dominant, then they protect your signals from destroyed. Yes, so again, you have the very strong signal output, even in the sink, probably. So so we all see it's very challenging in the fluid domain, but still there are quite some work that has been contributing to the real part. Like in the audience, there are two guys. They have been doing lots of work, like Van der Molen and also Abdul Aziz. They have been doing lots of work in the Bighorn Basin. That's also a very important basis for my work. Yeah, so I guess you would also be amazed if you are in the field seeing all these kinds of regular red beds. So when you have the dating, tools available, so sometimes you get the duration of those cycles very close to some orbital forcing. So I mean that would be natural. Then you think they have the astronomical origin. So here you can see this big boundary sandstone is a PTM boundary sandstone that separates the Paleocene from Eocene. And below that we have the Paleocene record. Then on the top of it we have the Eocene. And my study interval is mainly in the Eocene. You see it's more reddish than Paleocene. And you see all these kind of trenches. That's all the work done by my supervisor like in 10 years ago. Yeah, they are just destroying the beautiful outcrops. Yeah, probably you would underestimate how large is this scale, but here I have a picture for you to see. You see there's a human in the circle, so there's quite big outcrop profile, so we can do quite much work based on this section. Yeah, so in 2013, Hemel Abels et al. They filter the power, they filter the proxy of the lightness, also the redness. Then they have this kind of curve indicating the presence of precession. Sometimes you also see there. Oh, sorry. Yeah, so sometimes you also see some like weak peak. that might indicate the presence of eccentricity that are like larger cycles. Okay, so now a very simple assumption is whether we can somehow reproduce this kind of cyclicity. Yeah, so you have seen the results. Yes. So what I'm using is using some numerical model that's process-based. So you put the water and sediment in, then everything is feeding the basin. You have the base level rise that provides the accommodation space. So the rivers work in between to make some deposits. Also, you see the alluvial stratigraphy. I will later show you. Yes, so here is a nice animation showing how the cyclic inputs can be preserved in the alluvial stratigraphy. You can see on the very left part, so we have a cycle in the boundary input QSQW. Then you can see also in the, Yeah, so here you can see these channels are building up now, then building, filling up. Again, some super elevation is reached. Then it moves to the other location, so kind of the erosion. So in this way, we can see the channels, sometimes they are stable, and also you see those all the black lines indicating hiatus or non-deposition. But in the other phase, you have very fast aggregating lines that indicating erosion phase. Yes, so at this stage, we can say we kind of reproducing the cycles we observe in the field. Here you can see there are roughly 4 cycles. You see there are some like channels kind of thing here. Also the lateral is very black. That means non-deposition during this phase. Yeah, so then we do more extensive work. I will not bother you here. So the main thing we are working on is the amplitude and also the wavelength. So as you can see from up to down, so the amplitude becomes larger and larger. So you can see clearer separation between the overbound phase, also the erosion phase. Here you can also see the kind of Taylor diagram. Also you can see it's in the power extra peaks. The peaks become stronger and stronger. So we say a larger amplitude may contribute to better preserved signal. In the right, you see the wavelength scenarios. So this is quite complex. If you are in physics, you can go to my papers. But now I give you the conclusion. So when you have higher, so in the right, the legend of color indicates the chance of signal preservation. When you have more greener, so the signals are better preserved. When you have larger amplitude, signals are more preserved. But for the wavelength, it has to be within a certain range. Yeah, so we can also see those climatically forced transgression and regression. You can see here, so the red dots indicate where the base level reaches the land surface. Sometimes you see the regression, then transgression, regression, transgression. That's very typical sequence photography images. So on the right, it's also possible to calculate the compositional stacking because you are able to, because we have perfect time control of each timeline, so we can do a lot. Yeah, then we come to the second part, maybe third part, on the outcrop results. So we would first focus on the paleosoils as the cycle boundary layers. Then we go to the channelized sandstone bodies. Then finally, we integrate them together to see the stratigraphic relationship. Okay, but why are we keen on this? Because normally, many people, they work on 1D data. Imagine you only have 3 wells with different phases, paleosoils, also hydrolytic deposits, also channelized sandstones. So there might be many options when you are trying to interpret or correlate. But people now even don't know what the simple situation is. Okay, so if we have some outcrop analog that can help for the subsurface data. Okay, so we have 3 scenarios. Maybe so the upper 2 are the 2 end members. The upper one is very allergenic and regular. Then the middle one is more random, chaotic. But when these 2 are combining together, you may see the regularity, also the randomness. So based on this, what we want to quantify is to work on these paleosoil layers, those orange ones, also those channelized sandstone bodies, to see how they how they relate to each other. Yes, so the first part is to trace all those paleosoil layers. Here you can see a beautiful outcrop with many strong paleosoils, and on the upper right you see the red and white, so they make up of one cycle. So in the vertical section you may have multiple cycles. So how do we do that? Normally people do it in 1D, but in 1D, you know, so due to the autogenic thing, you may have very strong variability. So now we are lucky. We have some drone model. This is a very large model. It's about 10 kilometers, so 10 square kilometers. So you can do all you want in the model, like tracing all the lines, all the paleosoil layers. You can trace them over several kilometers. Then you can also make the digital sections. So basically, you can imagining you are printing on the surface. So you can do a lot in 3D. Of course, there are also many sandstone bodies. Then you can relate them laterally, so to see how they are sitting in the stratigraphy. Yes. So this is the model we did. Yeah. So there are many other analyses like variogram, like the other calculations, but they are in the paper. If you want, you can find them. Yeah, then we come to the sandstone body data. Yeah, we document a lot of the data, both in the field and also using the model. So those yellow stars indicate where we stop in the mountains. We describe, we log, then we do lots of work there. Then later when we come back to home, so we use those models. You see the white lines that are covered. So that are covered by the drone model. So you can classify the sandstone bodies you see, and then do more calculations, like measuring the dimensions. Yeah. So here I show some examples of the sinuous channels. Here you see Youwei storms and also Dirk Yang. They are also helping me measuring the sandstone bodies. Yeah. So basically, this is a very typical point bar. We call this one #1 point bar because this is so beautiful. Yes. So there are some analogs of kind of like modern meandering system. The one on the left is like the simulation. So on the right we see the landscape evolution over only a few tens of years. Then the other one we see is the braided channel. You can see the braided channel is a bit different from the meandering one, because they have multiple story. Normally they can be formed in the flashy discharge or maybe higher discharge due to they have very strong power. Yes, we also have modern analogs, both in nature, also you can create it in the film. So it's quite nice to compare them. But always keep in mind, the surfaces process, they are not always preserved in the stratigraphy. So sometimes when we are comparing the processes with the product, we have always to be cautious. Okay, now we compare a bit the difference between the two little stars. Yeah, so they are different in different ways, but sometimes it's more different, sometimes less. Then our main purpose is to see how are they sitting in the stratigraphy. So here you can see there are many labels and also green dots. Each gray dot indicates the position of one channel sandstone body. Then we can project them in 3D because we have the geo-reference coordinates. So here it's like the 3D projection, but it will be chaotic if you project it in 3D. So we project it onto three different planes, and we are lucky to find that there's one plane, the YZ plane along the flow direction. We have a very strong meandering belt, and that can be used to readjust this profile a bit, so you can see it. So at least there is one like meandering dominated interval, and also one braided dominated one. Yes. So based on these results and also borrowing the results from the others, then we reconstruct the model for the Bighorn Basin. Yes. So basically the red rectangular indicates where our area is. It's quite a small area, so we have to borrow many results from the others. to improve our model. Yeah. Then later come to the exciting part. Now we have to do it manually. We find one sunstone body, then we put it in the stratigraphy, then we see how they relate to each other and also to the paleosoil layers. Here you can see each horizontal line is one precession cycle boundary. Then you see there are many channelized sandstone bodies on the top. And these blue guys indicate seniors bodies, and then the orange ones indicate indicated braided bodies. But now on the right, you see that, so they are the curve from the astronomical solution and also based on the other proxy. So, but we can see there are clearly two intervals at least. One interval, this interval, the lower one, dominated by the seniors bodies. Then the upper one dominated by braided bodies. And also they coincide well with the eccentricity maximum and minimum. So if we conclude, summarize a bit, so we see the seniors dominated intervals in the eccentricity maximum. That's not what we normally expected, because normally when you have the maximum, we have very strong seasonality, we have flashy discharge, but now we just observe it here. But then in the eccentricity minimum, we see the braided dominated interval. Probably it's due to the high discharge throughout the year, but more evidence is needed. Yes, so basically the academic part has been finished. Now I think most audience are curious what we are doing in the field. Yeah, it's quite fun and also exhausting. Yeah. So first of all, in the morning, we first have our coffee and breakfast. Also toilet, you know. You have a shower, you go somewhere to find a toilet yourself. Yeah, like everywhere. Yeah, then we test the drone a bit sometimes to see whether everything is working well. Then we plan our trips in the map. So sometime, before the day, we already know where we are going. So it's, smarter to not waste your time just finding something. Yeah, then later we go down the hill, take some group photo. Yeah. So Youwei is teaching me how to do the measurements, and I'm logging. I'm also describing. Yeah, basically that's the work. On the very left, you see I'm really working hard to dig a flat surface section. Then also many people are working on the cliff. Yeah, as Hamel and me are discussing on our observation in the field. Then this is my best field mates, team bars in the field. Yeah, so this basin is also full of fossils. So every year, many people are distracted by the fossils. They forget the work, like this guy. Yeah, this guy is always finding the fossils. Yeah, so 10 years ago, he already found a drawer like the fire dog. Then every year, he keeps finding new things, and like others also, you're also keen in this. Yeah, then we come back for the dinner. Yeah, we alternate to cook. Sometimes it's Western style, sometimes Chinese style, but we always enjoy that after a long day. Yeah, then later we charge the drone batteries, because every day we can use up to 10 batteries for the flight. Then we do the dishes together. You see Youwei is very happy doing the dishes. Yeah. Then finally, after 1 week's work, now we are going down for the rest day, normally on Friday night. So we drive down to the house of a local professor, who is also a professor in the Michigan. Yeah, then there are some guys stopping us, hey, is that time for us? You should keep working. Yeah, but anyway, we just go. Yeah, finally we have the rest day, we cook the dinner together. And one day I cook it with my friend Chao Wang. With many dishes, and Philip is a bit impressed, and he made a toast. Yeah, there are also some group photos we have. Yeah, this Hiranya, also very nice mate of my fieldwork. Yeah, basically that's all. Thank you for listening. Okay, so for those who don't know the schedule, so now we have 10 minutes for some rest, then at 3 o'clock sharp, will start the official defense. So there will be committee members both online and also sitting in front of me. They will just attack me. I will defend myself. If I need your help, I will let you know. Okay, thank you. If you have some questions, you can also ask me or later. And after the defense, there will be a reception in aula. You can follow the mass so you know where it is.
Ik open de zitting van de commissie ter beoordeling van een proefschrift en de stellingen van Youwei Wang, Master of Engineering in Geological Resources and Geological Engineering from the China University of Petroleum. De verdediging zal in het Engels worden gevoerd. I request the promovendus to go to the lectern. A warm welcome for all of you at the public defense by the candidate of the dissertation entitled Alluvial Stratigraphic Response to Astronomical Climate Change, Numerical Modeling and Outcrop Study in the Bighorn Basin, Wyoming, USA. The Board for Doctorates of the Delft University of Technology has installed a committee to evaluate the dissertation and propositions. The committee will have a debate with the candidate in public. It's an honor for me to present the members for this committee to whom I extend a hearty welcome. First opponent, so on the screen he is on the right side, that is Professor Fielding from University of Connecticut. He is from Geosciences. Second opponent, also online, is on the left part of the screen, Professor Hampson from Imperial College London, Department of Earth Sciences and Engineering. Welcome. Then we have here in the room, on my right position, so first Professor Kuiper, she is from Vrije Universiteit Amsterdam, Department of Earth Sciences. Then next to her, Dr. Stouthammer, Utrecht University, Department of Physical Geography. Other members are all from the Delft University of Technology and from the Faculty of Civil Engineering and Geosciences. On closest to the public, we have Professor Bertotti. And then on my left-hand side, first Dr. Abels as promoter, and at the far left, Professor Martinius, also promoter. Thank you all for taking part in this academic ceremony. My name is Kees Fuik. I'm a professor of applied mathematics, and it's my pleasure to chair this session on behalf of the Rector Magnificus. I would now like to start the opposition and give the words to the first opponent, Professor Fielding. The floor is yours.
For the promovendus, Youwei, nice to meet you. I'm sorry I couldn't be there in person. Congratulations on an excellent job. I've seen the final version of the dissertation and it's a beautiful piece of work. I haven't yet seen the hard copy, but I'm sure I will once the US Postal Service delivers it, and I will treasure it. Thank you for sending it to me. So I have some questions. As you know, my interests mostly pertain to Fassi's models and the development of interpretations of ancient depositional environments. And I was very taken by your identification of 4 different channel body styles. And you'll recall, because we have had a conversation about this already with your draft thesis, that I wondered how you saw these different channel styles perhaps coexisting. I also know that you, in your stratigraphy chapter, you talked about different styles being representative of different phases, perhaps, of a cycle of orbitally driven climate change. But I wonder, since the bodies are not that different from each other, to what extent do you think they might coexist? And I'm speaking specifically about the sinuous versus braided versus trunk channel bodies.
Bade promovendus, is the question clear?
Yes.
Please defend your thesis.
Okay. Earlier opponent, thank you for your question. Yeah, I think this is a very good question to think about whether it's, reasonable to attribute different river styles to the dominance of that stratigraphy. Yeah, so what we have seen in the field is those braided and sinuous river bodies, they are quite different from each other. Although the numbers are a bit similar, sometimes they are not significantly different from each other. But what I'm seeing is, so I assume all the rivers are forming a continuum from the upstream to the downstream. But now we are not claiming each river style are changing per cycle. So that means there could be coexistence of different river styles in one, probably like in one precession cycle. They could coexist. But sometimes there's a dominance of one river style. Like you clearly see it in the stratigraphic chapter, you can see the braided dominant interval and also sinuous dominant interval. But I mean, in the meantime, you also see they are not alone. They are coexisting with the others. Yeah.
I think that's entirely reasonable, given that if you look at modern rivers on satellite imagery, often they change their style even along the length of one river, even over short distances, or they change their style at different discharges according to how much water is being transmitted. So I think that's a reasonable position. Excuse me. Let me ask you, following on from that question, you did entertain the idea that the different styles and changes in them may be modulated by the changes in the discharge regime, and you noted this is in the later chapter, the stratigraphy chapter, that the more representatives of more flashy discharges might record eccentricity minima within your cycle. Could you explain how that works?
Okay. Yes, thank you. This is a very good and also challenging question. Yeah. So now I mean, to be honest, I'm also very puzzled by this phenomena. Now we observe the sinuous bodies in the eccentricity maximum. Normally, we would expect this to happen in the minimum. I mean, according to our straightforward understanding, because normally the maximum has a stronger seasonality. We would expect more flashy discharge. But now I'm thinking probably the discharge is already quite high in the maximum. So even though the variability is high, but still is maybe this is already high. The variability is also high, but they stay high. So that makes a perennial discharge conditions that favors meandering to be developed. And also in the meantime, in the eccentricity minimum, normally we have like smaller seasonality. That means the precipitation may not changing much. So we all know that the river style is also a function of the down valley slope and also discharge. Maybe in this time the variability is small, but the discharge is relatively high. So I think the high discharge might be an important condition to form the braided rivers. Yes, thank you.
Okay, thank you. Let me ask you about your proposition 2, if I may.
Yeah.
Waarde promovendus, can you please read proposition number 2?
Yes. Okay. With more gaps than records, fluvial sediments still provide a natural lab to observe interactions between allergenic and autogenic forcing at certain temporal and spatial scales.
Thank you.
Okay, and of course everyone agrees with that statement that the stratigraphic record is notoriously incomplete, particularly so for fluvial successions. That's been established widely. So let me ask you, how complete do you think your succession is? Is there any way of interrogating how complete your succession is, and where would you go perhaps to find a more complete succession?
Okay, so if I understand your question, you're asking me whether there are some other basins with more complete preserved cycles similarly to...
That's the second part. The first part is, do you have a feel for how complete succession you studied is?
Okay, I see. Yeah, so this is a very good question. Yeah, like I just showed it in the layman's talk, we all know the Sadler effect. So I mean, particularly in the river part, the gaps are more than the records. So yeah, so it's always challenging to do the cyclostratigraphy in the river domain because they are less favored than the marine and the Lacustrine domain, where the sedimentation is more continuous and also the product is more complete. But now what we are looking at is not like a very sub-precision scale thing. So we don't need it to be very continuous. Instead, we look into packages like one channel stability phase and the other one channel instability phase. So we combine these two phases at one cycle, then we do that. Then we analyze it. So sometimes it's a bit different from the traditional stratigraphic work because we have to work on a certain scale instead of making measurements at very continuous measurements.
Okay,
Yes,
thank you.
then your second question is where can we find some other basins? Yeah, this is also a very good puzzle for me. I always say that to my supervisor, Hemel Abels. I say Bighorn Basin is quite a unique basin. Probably it's one end member in the world. Then he always said, I'm afraid, so I'm not sure. But I think, so to my knowledge, it's a very key condition to have all the cycles preserved if we have the continuous accommodation space created either by subsidence or by base level. And also Bighorn Basin is quite unique because we didn't see much base level, but instead the basin subsidence is more important. And also we see that in the numerical models, only if we give the accommodation by rising the base level, then we can preserve more cycles. Otherwise, they will be destroyed by the autogenics.
Well, thank you. And that concludes my questions.
Thank you very much for the opposition. Then we go to
Thank
the
you.
next opponent, Professor Hampson.
Okay, Vada Promovendus. It's good to see you, Youwei. We've also kind of swapped emails about your work earlier, and I think you've got a very nice thesis. You've done lots of really nice work, lots of different techniques that you've been able to integrate together to give a nice sort of coherent picture and to use those techniques to their best advantage to test against each other. So I think you should feel very happy with the work you've done, and it's good also to see it being published as well.
Yes, thank you.
So I have some questions really around the origin of some of the stratigraphic cycles that you've described, and maybe thinking about what other possible interpretations might be possible. So my first question is, the stratigraphic cycles that you've described, they're all driven by climate, all interpreted to be driven by climate and therefore to be allergenic. Do you think it's possible some of those could be autogenic, driven by processes within the river systems? And is that a possibility, and what would you look for to distinguish those two different mechanisms?
Yeah. Opponent, yes, thank you for your question. Yeah, this is a very good question, and also there's always strong debate between different people within our community. Some people may think it's fully autogenic, while some others insist it's only allergenic. Yeah, but yesterday there was just a talk organized by the Sales Online. So what they say is, so could that be the case? Autogenic is part of the spectrum of the allergenic. Yeah, so to me this is a very interesting topic as well. So there are people debating for each side. Yeah, but I think it could be possible. There are some autogenic cycles. Yeah, in my thesis I also show compositional stacking. So a basin, if everything is keeping constant, then there would be a time then the sediments is feeding all over the basin. Then again, another cycle comes. Yeah, so we would call this autogenic cycle. Yeah, but in the Bighorn Basin, I mean, based on the dating results, they have the very similar close duration to the precession cycle wavelengths, like 20,000 years. So I don't think this is a very coincidence. If you keep seeing them in the stratigraphy, they are repeating so they keep repeating and also always have the same of very similar duration to that wavelength. So I would think at least in the Bighorn Basin, it's more allergenically driven.
Okay, so that would be, that argument then is based on the duration of each cycle. You mentioned compensational stacking. So the cycles you've mapped out, most of them extend over the field area. Is
Yes.
that correct?
Yes,
So-
but so I also did some calculation based on the numerical modeling data set. And also I clearly see when there's no allergenic forcing, there will be some compensational timescale. People may also refer it to autogenic timescale. But when there is allergenic forcing present, then they will be interacting with each other, and the autogenic timescale will also be prolonged to a larger time, to a larger number.
Okay. So, I mean, another way of approaching that question would be to look at the areal extent, the geographical extent of the cycles that you map out. And obviously, you know, you've done a great job of mapping out these cycles in a really nice field data set, but there's no field data set where you see everything. So do you have how much of the Bighorn Basin do you think you sampled within your field area?
Yes, this is a very good question. Like, what our observation is representative of the basin? Yeah, our feed site is relatively in the northern part of the basin, so it's quite a small area. Although we claim it's large, it's 10 square kilometer with our drone model, but compared to the basin, it's still very small. Yeah, so I think when we talk about the cycle preservation, what I showed in the numerical modeling, so the chances of cycle preservation get lower when you go downstream. So if you see that already in quite downstream, then you would expect there are stronger cycles in the upstream. So I think, so according to our field observation in our field area, probably there are also other cycles in the upstream. But unfortunately, the very upstream part of even middle stream part, they are all eroded. So the wellwood formation is only partly outcropped. So that's a pity for us to check our hypothesis.
Okay, but so it sounds like you think it may be likely that if you could sample a bigger area, you would see more cycles and maybe start to pick up maybe more of an autogenic signal locally.
Yeah.
Yeah. Okay. So that's a good answers, and it's a difficult question to address. So but it's good that you're aware of the debate around it. So I have some other questions around the field data that you collected. So, and obviously I imagine your fieldwork plans were disrupted by the pandemic, and probably things have been a bit different than you maybe envisaged the last couple of years. So one of them is really maybe more of a mechanical question, but how long did it take you to collect the field data, to process and map out the stratigraphic cycles, and what sort of confidence do you have in the interpretation that you generate?
Okay. Yeah. So this is also a very good question. Yeah. So before the pandemic, I'm lucky to have been to the Bighorn Basin for 3 years, so successively. And in the first year, to be honest, I was flying with my supervisor, the drone, but I mean, clearly we didn't know the trick. So in the first year, it's not very successful. Then in the second year, we know it's better to hire like a professional. So we contact Professor John Howell from Aberdeen. So they send out a pilot to fly the drone for us. And then, I mean, since she's so skilled, she finished everything, I think roughly in 2 weeks. Then she again spent another some weeks for the post-processing. Yeah, but that's her work. My work is to collaborating with my supervisors and also my office mate team bars. So we are doing the correlation independently. But finally, if we start from different sides of the model, then we meet somewhere in the middle. But I mean, at the beginning, we are based on the fringe sections my supervisor made like 10 years ago. So you clearly see the fresh rock surface. So we are certain what we are seeing is also reflecting what's in the fresh surface. Then we do the independent correlation. So finally, we 3 people decide whether we agree with each other, and we make some adjustments to do that. So it takes us quite some time, maybe a few months, to map all the 44 cycles in the 300 meters photography. Yeah, in the model you will see it's full of lines. If you look at a distance, it's a mess. So it's quite some work. Yeah.
So did you find that the three of you disagreed a lot, or did you have quite common findings when you came to join up your mapped areas?
Yeah. So my supervisor is always more stubborn than us. So sometimes we have to really discuss a bit whether we think this is a layer or that is a layer. But clearly he has more experience. But after the explanation, discussion, then we settle down. Then so in most cases it might be a shifting up and down, but finally they will be quite convergent in the middle.
So what was the cause of these difficulties then? I mean, which bits of the outcrop data are you less confident in interpreting that gives rise to these differences?
Yes, so this is again a very good question, because here in the model, although the model resolution is overall very nice, but still you have some areas with lower resolution. We always first try to find individual photos also from the drone, also from our handheld cameras, but sometimes really impossible because you only have some fixed angle to look at the outcrop. So, and also sometimes there are some vegetation on it, some debris covering the outcrop. So in many cases, and also a very, sometimes annoying guy is a sandstone body, because when they are present, so all the areas surrounding that, the soil are not very developed. So you have to make a jump from this side to the other side of the sandstone. So this is the most guess we have to make. But normally if you see, different soil layers may have different properties, because sometimes they are not like single soil, sometimes they are composite. So different soil bodies have different properties. So we can, in many cases, make the confident jump. But in other cases, we have to rely on tracing them in 3D to see the regularity.
Okay, so that leads me on nicely to what I think would be my last question, and that's on your proposition number 1. So,
Waarde promovendus, can you please read proposition number 1?
Yes. Okay. Youwei-based photographic models are superb for geologists in the new area, but they can never replace the real field survey.
Thank you.
Thank you.
yeah, so based on that, I mean, what would you say are the big strengths of the drone data sets, and what are the big strengths of the real on the ground field survey?
Yeah, okay. Yes, thank you, Professor. Yes, I know your point, because I have seen your fieldwork presentation for the, bachelor master students in the Imperial College. Yeah, I know. So I think with the drone model, we are more confident with the 3D, because when you are in the field, normally it's not possible to standing on every point, as you want. In many cases, you have to find a location where it's safe, it's also accessible, and also, so for some angles, you really need the drone to do the work. Then you can also trace many layers over several kilometers in the drone model. That's not possible by humans working in the field. But in the meantime, the field geology work is also not replaceable, because humans are still cannot be replaced by the machines. And also the vegetation, the weathering, everything on the surface may fool us. You may think this is something like that, but when you dig a fresh surface, you see different things. So we really have to do both, including both in-house work and also in the field.
Okay, thanks very much. That's my last question, and I hope we both get a chance to go out in the field sometime and test this.
Okay, thank you very much.
Thank you. Then we go to the next opponent, and I give the floor to Professor Kuiper.
Waarde promovendus, I also would like to congratulate you with your thesis. It was a real joy to read it, and even without fieldwork in the last years of your project, I think you really did a nice, really nice job. And I find especially chapter 4 and 5 very intriguing because you try to make a link between the channel deposits and astronomical forcing based on field data, while in the past we mainly looked at overbank deposits, so that's really something new and complicated. So I first like to go to page 80 of your thesis and your paleogeographic model of the Bighorn Basin. And after the questions of Professor Fielding, I was wondering, did you also look into the provenance of your sandstones? And is the provenance between the sinuous deposits and the braided river deposits different?
Okay. Geleerde opponent, thank you for your question. Yeah, so this is a very good question and also a very important way to think about the catchment of the province. Yeah, so we did have some files. Yeah, on page 72. Yeah, so our files is to look at the mineral difference in different river, in different channel bodies. So clearly, but now, I mean, for the samples we have, so we find the sinuous bodies, normally they have finer materials, better sorting, but for the braided ones, they are coarser and also they are more angular. But I mean, unfortunately, our last fieldwork in 2019, in that field campaign, we only collect a few samples, like maybe 40. But before that, we really don't know what river style so we are looking at. Then we only have three sinuous body samples, and also more than 30 for the braided. So clearly, we don't have a large enough number to confidently say we know they are coming from different catchment.
Yeah. So in the future, you like to go back, sample more sandstone bodies, and also do some provenance work.
Yes,
and
yes, for sure.
What type of provenance work would you think of?
Yeah, I think, to be honest, so the world formation is mostly eroded. And also, there is a very important provenance in the southwest, but now covered by the volcanics. So to me, I would think they may have different properties, either from south sharp or from the west, or maybe like southwest. But they have different materials. They may have different minerals. Yeah, so that's what I'm thinking. But still, it's not very possible to collect a sample from the catchment.
Okay, I personally would recommend to try a pilot on provenance dating. So I saw you have some microclines, some micas in these samples. So and the volcanism in the area is different in age. So maybe with provenance dating you can get an idea of the provenance of your sandstones.
Yes.
That's something for the future.
Yes.
So now I'd like to take you to your figure 412 on page 77. And there you've plotted your braided sandstone bodies and your sinuous sandstone bodies in X, Y, Z space. And in chapter 5, you plot these in figure 5.3 in against time. So basically these are the same data, the one plotted against depth and the other one against time. And I was kind of struggling to find all the points back that I see in figure 412 in figure 453. So I was wondering if you could explain to me how you exactly did this. Because if I look at 412 at level 1500 meter, Z level, I see a lot of blue dots aligned, and also at 1560 I see a couple of blue dots aligned, and I don't see this double alignment back in figure 5.3. So please, can you explain how you arrived from 412 to 5.3?
Okay, yeah. Okay, thank you for your question. Yeah, so there are different ways of plotting them into the stratigraphy. The first one is the automatic way. Basically, in the figure of 4.12, so I use some algorithm to just project them. So this is without any human interference. So basically, I plot the coordinates. Sometimes they are higher, sometimes they are lower. But I mean, in the field area, there are some faults Also, there are some tilting of the strata due to the later reworking or maybe tectonics. So sometimes it's not very straightforward to directly plot them. Okay, maybe first back to your first question, how I do that. First, when I see a sandstone body, so I put a point on both on the top and also in the middle of the sandstone body. So this is the coordinates for this sandstone body. So I have all the 3D data of them, then I directly project them. Then we see the tilting, then we do that, but for the force, we really cannot do it with the algorithm. Then later, so this is very easy and fast for the 4.12, but for the one in chapter 5, it's really time consuming. We do it manually. We trace one paleosoil layer laterally, then we see this sandstone body is more or less, although we are not 100% sure this is on this level, but we do our most educated guess. This is on this level. So sometimes there are many adjustments.
And you do that on basis of the model you made, or do you do that on basis of what you see in the field?
So based on the model.
Okay.
Yeah. And also you ask why there are many braided in this interval but not in that. Yeah, sometimes the dots in the 4.12, they seem to be a lot. But indeed, in the chapter 5, they are very smaller in dimension. So the numbers count, but the dimension are much smaller than the other bodies. So yeah, so that's the difference between this figure and that figure. And also, to be honest, chapter 5 figure is more mature than that one in chapter 4.
I really like the figure.
Yes.
And then I also want to jump to the next figure, 5.4, because this is the result of your numerical model.
Yeah.
And I was wondering, your figure 5.3, do you think it looks like 5.4a or b? And would there also be a way to somehow quantify that?
Yeah. So thank you for your question. Yeah, there are lots of debates even between me and my promoters. They are not fully convinced by my statement, although finally I write it anyway here. So to me, what I'm thinking is, if you look at figure 5.4, there are two different scenarios. So the upper one is fully autogenic. Yeah. That means there's no cycles acting on it. But you see the channel bodies, they are everywhere. They are scattering throughout the stratigraphy. But if you look at the lower panel, so the channels, they are mostly in the overbound phase with very strong development, also long lifetime. So what I'm thinking is maybe braided rivers, they are more aggregating constantly. But the sinuous rivers, they are really formed. So they are first eroding, then so all the flow are concentrated in the valley in the channel. Then in another phase, when the QSQW of sediments concentration increase, they start to filling the channels, become super elevated, then they go left and right toward walls. So to me, what I'm seeing is braided is more close to an autogenic scenario, but sinuous one probably is stronger than in the allogenic scenario. If you look at figure 2.9, so from up to down, the signal amplitude becomes larger and larger, then channel depths become also thicker and thicker. So what I'm thinking is probably the meandering of sinuous bodies, they are more related to this kind of high amplitude cycles. That's the reason why they are in the eccentricity maximum. So the overbound phase and also the water phase are clearly separated due to this high amplitude in the sediment concentration modulated by eccentricity.
Okay. Then I have a question that I already asked you before, and you had to think about it, so I'm curious if you have thought about it. On page 93, you state that eccentricity may directly influence local climates as amplitude modulator of precision, and thus influence water and discharge and sediment load. But later you state you are not sufficiently confident to relate the observed changes to either local eccentricity controls via seasonality changes or global eccentricity related climate changes. And I was wondering if you can explain what you mean with difference in local eccentricity control versus global eccentricity control. How can you make this distinction?
Okay, thank you for your question. Yeah, this is indeed a very good question. So we don't always see this kind of cyclicity in every basin, in every area, probably because each basin has its own settings, own properties of the basin. But I think for some local, so what I mean here, the local eccentricity may mean when you have some maybe insolation curve that's caused by the eccentricity that can be felt by the catchment area, then they flow down the mountains, they form the rivers, finally they get deposit. But when I say global, that means already the whole Earth is experiencing the eccentricity change. For instance, the global temperature rise in the same time, the global precipitation rise or fall in the same time. But sometimes it's not. For instance, the most known PTM event, so the global temperature has been rising for 6 to 8 degrees, but not every area on the Earth have the warming event. Some area even become cooler. So that means something local thing, sometimes they can outwin the global events. Also another good example is the Asian monsoon. We all know, so the monsoon system, for instance, in the north, they are more controlled by the high latitudes, like maybe glacial, interglacial cycles. So that's more controlled by obliquity. But in the south, we have more precession controlled because they are in the low latitude. So in the same country, over a large range of the latitudes, you will see different phenomena. That means local and global things, they are not always consistent with each other.
Okay, thank you. Do I have time for another one, or?
Maybe better.
Yeah.
Thank you.
Thank you very much for the opposition. Then I go to the next opponent and I give the floor to Dr. Stouthamer.
Thank you. Waarde promovendus. First, I would like to congratulate you with your thesis and the extensive research that you carried out. The thesis was really very pleasant to read and also very nicely illustrated, which helped a lot to clearly understand the text. And also the subject of your thesis obviously is very challenging because it's not easy to unravel and that's a bit of an understatement, to unravel the alluvial stratigraphic response due to astronomical climate change from the sedimentary record. But in the end, if we are able to unravel this greatly contributes to our understanding of how fluvial systems react to astronomical climate change and how this is reflected and preserved in the sedimentary record. So I think your work really contributes to that. And what I would like to ask you some questions about is about the numerical modeling that you did and that you described in chapter 2. There you evaluated the impact of cyclic and non-cyclic upstream climate changes on the alluvial stratigraphy by using the process-based alluvial model developed by Derek Karsenberg and John Bridge, which I think is a good way to get a grip on this and to increase our understanding. However, as most of us in this room know, a model per definition is an approximation of reality because of limitations in our knowledge, data availability and the modeling itself. So I have a few questions regarding the model setup specifically and the consequences of the chosen setup for the results and application to the Bighorn Basin, your fieldwork area. So you modeled a rectangular basin of 60 kilometers long and 40 kilometers wide, as you state on page 12 and illustrated that in figure 2.1. But why did you choose for these specific dimensions? Because the Bighorn Basin is circa 200 kilometers long and 80 kilometers wide. Could you please answer this first question?
Dear colleague, opponent, thank you for your question. Yeah, this is a very good question, and this also has been raised by the other committee members. So also, it's always challenging to directly compare our numerical model with the field data, because there are so many things different and also so many things unknown. So what we are doing now is to make a qualitative comparison. So using our numerical model to compare it with the field. So why I put 60 by 40? So I mean this number can be any number, but the key thing is we have to make the model run. The model has to be stable. So the trick when you are playing with the model is that, for instance, this is the basin slope. You fit the water discharge in. In this part, you have the base level rise to create the accommodation space. So this number is also like closely matching with this area and also the sediment input. So basically, it's not very fair to compare the model with the field because the model is perfect. Now if you divide the sediment volume in cubic meters by this area, you will have 0.4. That's exactly the base level rise rate. So that means the sediment feeding the basin is the same as the base level rising. So eventually, the sedimentation rate would match the base level rise rate over a long term. But how long is this depending on the basin size, the discharge, sediment, base level rise rate? Yeah, so this number, I mean, is not very important. You can make it every number, but I mean, given the capacity of our computer, we just find this number. And also this number, to be honest, is the default number used by Derek in the 2008 model.
Yeah, what I expected that you, because I calculated that, is that you would take at least the same ratio. So the length relative to the width of the basin.
Yeah.
So, but but you didn't because it's 2.5 in reality and 1.5 in your model. But what do you expect to be the effect on the results of choosing for a rectangular basin in this case, and also these dimensions? So, yeah, and with this form. So, in other words, how would the result change if you would choose other dimensions or even another form and keep the other boundary conditions the same?
Okay, thank you. So this is again a very good question. Yeah, I have tried, I mean, I have played with this model for almost 3 years. So I have tried every possible scenario. Yeah, now for instance, our basin like this, you would expect something like this. Yeah, so what I have learned from the literature is this length from upstream to downstream that determines, yeah, so they have something called autogenic time scale. They use this length square divided by maybe the feeding rate of the sediment. So that means if you have different values for this length, then the basin may fill maybe, maybe the sedimentation would not reach the compensational state. No. I mean, in different ways. And also, if in this way, they have to go lateral and right, they have to fill different parts of the basin. But I think this length is more important.
Yeah, so it will have really consequences for the distribution of the clastic sediment. And that brings me to the next question. Because the model considers sediment transport, erosion, and deposition of clastic sediment. So the model does not take into account peat formation in the flood basins. So my question is, what do you expect to be the effect on the result if peat formation would be added to the model?
Yes, this is a very nice question, and also this is a problem for our field data. Yeah, so like maybe I first say something about the field data, then I come back to your question. In our drone model, although we trace nicely so along the perisoil layers, but they really show very strong variability due to compaction. But I mean, that's the same case in the core layers. They may be initially very, very thick, but later they are compressed to probably a very small number. So I think it will be very nice to include this in the model But also in the meantime, I think this will also change the conversational time stacking, because this full-on autogenic thing is really interfering as the allergenic signals. So I think that will make a big difference if the compaction is really big.
Yeah, I think it of course has an influence on the position of channel belts. That leads to fixation, but also on the eventual geometry, for example.
Yeah.
So and that is something you might see reflected in the alluvial architecture.
Yeah.
So, but indeed, this would be a next step, and this is also a very challenging step. This something to be worked on in the near future. And then my last question. So, what's your opinion about the applicability of your model calculations to the Bighorn Basin study area and to other basins?
Yeah. So I think Gary of Chris has asked this thing, so whether we can apply this model to the other basins. Yeah, I'm thinking Bighorn Basin is quite, maybe I'm too much poor in knowing the other basins, but Bighorn Basin is quite ideal to do this kind of work. And also the accommodation space is very critical to preserve all these cycles. If you have some, uplifting things like that, up and down, then all the deposits will be removed. But I think it may be very favored in a foreland basin where the tectonic substance is quick and you have enough time and space, maybe not time, but enough space to have it deposit. Yeah, but I need to find some other basins. Now I only know this one. I'm sorry.
No. You can only do one thing at a time. Yeah. So, thank you.
Thank you.
Thank you for the opposition. Then I go to the next opponent, Professor Bertotti. The floor is yours.
Thank you. Waarde promovendus. Thank you for inviting me to do this, to participate in this committee. It was interesting to read the thesis and I learned a lot, but not everything. So this is why I have a couple of questions. And I want to start from your figure 413, which for me as a kind of normal geologist does ring a bell. The first question is a bit the green, you have a green red trapezoid field there in the kind of the middle of the picture. Mm-hmm. That's your field work and your modeling work, is it correct? Because the caption doesn't say it must be somewhere in the text there. So what is the green trapezoid, no, the red square or kind of trapezoid which you have there?
Okay. So this would be like rectangular, but now it's kind of a bird view figure.
Yeah, okay.
Yeah. So that's our study area.
That's the modeling work you were discussing, the modeling?
No, it's not some numerical modeling. It's only the drone model.
And where is this corresponds roughly to the modeling area where you were discussing with Esther, or?
No. So our numerical model is just a kind of qualitative comparison with our field area. Our numerical model is actually comparing with the whole basin. But you can, now our data set generated is 3D. You can compare everything in the upstream, middle stream, downstream. Yeah.
I'm a bit lost here. You have in 2.1, your square, your rectangle there is, what was it, 40 by 60 or something like this?
Yeah.
And you produce some architecture.
Yeah.
But then on one side you say it could be everywhere, but the other side you compare it with this rectangle.
Yeah.
So it corresponds to this area.
Okay. Yeah.
No, I'm asking.
Okay. Yes, I know your point. Yeah. Okay. So overall, I'm numerical modeling the whole basin, but now we do a cross section. Maybe I show you here. Yeah. So
It's gone.
can you see my? No?
Oh, you can lift it.
Maybe not.
Okay, maybe it's too complicated.
Yeah. So now in 2.1, in figure 2.1, you see many lines, A, B, B, C, C, D, D, and those lines indicate different locations relative to upstream or downstream. Now what we are looking is line BB is more upstream. Yeah. So.
Okay.
Yeah. Basically, we are comparing this area with Bighorn Basin or with our field site.
Okay. Now, the discussion which we had already, is the creation of accommodation space.
Yeah.
And I really do not understand it in the sense that we say, because this is say the river flows towards the north, and where does it go? In a lake, in an indirect basin, and where does it go?
You mean in the
Did
model
it
or
go?
in the field?
No, in reality.
In the field, okay. In the field is
There is no sea around there, so
No,
there is no
no, no.
absolute level.
no. So if you look at figure 3.1, so the basin has an outlet in the north. So all the rivers, they flow out of the basin, and somewhere they enter the lake, but
Yeah.
not in the basin.
What I don't understand, you have a slope, which
Yeah.
is your 2.1, you have 6 meters over 60 kilometers.
Yeah.
And then you say you mimic a creation accommodation space by lifting the base
level.
level.
Yes.
And I don't see how this is possible, because, I mean, how does it work?
Okay.
If you bring your lake upward, the base level, it's a plain or it's a lake, what is it exactly? If it's a lake, then the lake should become larger, but for the rest of the area, nothing changes. So I don't see exactly how can you create accommodation space just making base level.
Yeah, okay. So I think there are two things. First is in our field area, there's indeed no base level, so we are more relying on the tectonic subsidence. But in the numerical model, in the available version developed by Derek Katzenberg, they don't have the basin subsidence module in it. So we have to make a compromise. We have to use the base level rise to create the accommodation space. I mean, ideally, this should be done by the tectonic subsidence.
But I don't understand how the model works. In a sense, probably somewhere your base level is probably a lake or something, and it should be a coastline. This coastline should move upward.
Yes. If you look at figure 2.8, figure 2.8, you see many red dots. These red dots indicate where the base level reaches the land. Basically, you see the red dots, sometimes they are migrating landward, sometimes they are migrating seaward.
I agree, but I don't see how this can create subsidence
Oh,
on the onshore part.
yeah. So I mean, if there are some
In the model,
Yeah, in the model, if you have some accommodation, if you have something below water, then you can accommodate. So the river profile will also adjust. If you have lower base level, for instance, so initially it's here, later comes to here, then the river profile will also go deeper. Then it also accommodates, maybe create some space for river deposition. If your river also rising, then you have less accommodation space, but still you can have some river deposits.
Okay, to be continued. I don't have much time, but I want to bring you to proposition number 9.
Waarde promovendus, can you please read proposition number 9?
Yes. Geology is philosophic, especially when you compare your life with that of a river.
Thank you.
Okay, it took me as a structural geology many years, but now I've discovered that there is various types of rivers. There is a torrent up at the mountain, braid. What are you then?
Okay, so now, yeah, so what I mean here, the rivers have different lifespans. So now I'm referring to a general river from the mountains to the sea. So like, I mean, when you are a baby or if you are a child, you are very dynamic, energetic, like the British rivers. They are eroding many.
When you're old like me?
No. Then you are.
And where are you then? Where are you?
Yeah,
Because
now-
the lake's different.
Yeah, now I'm in the transition between British to seniors rivers.
Oh, okay.
Yeah. So I can be also energetic, also a bit deep. Yeah, you know.
Thank you very much.
Thank you.
Thank you for the opposition. Then I give the word to the promoter, Dr. Abels.
Thank you. Waarde promovendus, it's my great pleasure to continue this very interesting discussion. I am wondering, you mentioned the Bighorn Basin is probably or maybe unique, maybe ideal, I heard you saying. I also heard you saying the stratigraphic record is probably more gap than records. So if the stratigraphic record is more gap than records, how can the Bighorn Basin be ideal?
Dear colleague, promoter, Thank you for your question. We have been discussing this for long, yeah. I think Bighorn Basin is unique in the sense that it has kind of constant tectonic substance. Although there are gaps due to river reworking, you know, river always rework, they carry the pre-existing sediments, but some of them below a certain limit, they can be permanently preserved. So what we are looking at is precession scale thing. For sub-precession scale dynamics, we are not able to do that due to these gaps.
So if you referred also to the Sattler effect, and you discussed that in the layman's talk, from your data and from your experience in the Bighorn Basin, where would be the first plateau reached, at what timescales?
This is a difficult question. Yeah, so there are some channels, maybe there are some channels that are really deep, so they may erode in the lower cycle. Sometimes, I mean, some cycles are missing, or maybe they are completely missing in our study area. So we have some miscounting. Now we say we have 44 cycles, but probably there can be more due to the erosion, or due to we are not able to recognize some cycles that are eroded by that. Back to your topic, the Sattler effect has some first increase and decrease. Yeah, in our model we have those plateau. So I think it's more in 1D, it's more common in 1D than in 3D, where you have some channels, active channels, they erode the other things, then the thing on top of it maybe form the plateau.
So, but at what time scale is the plateau?
Yeah, so now I think we are talking about sub-precession scale. I think in the overbound phase, that's very comparable. We have it in figure, yeah, I know you are referring to the fit case, but we have an estimation in figure 2.6. Yeah, so it ranged between, for the overbound phase, it ranged between like 40 to 60 in time.
You said sub-precession? Or
Yeah. So 40 to 60 of cycle wavelengths.
And as a very short last question, how does the trunk channel systems that and the model that you developed for that relate to accumulation rates and probably degradation in that view?
Yeah. Okay. So I mean, due to some influence of some philosophers, they highlight the continuum. So everything is not very different from each other, like you always told me that. So I'm thinking everything probably is in a smooth transition. Sinuous rivers, braided rivers, trunk rivers, also the other splays, maybe they are in a continuum. They are both continuum in the space, and also they can develop in a continuum way in the vertical. So I'm thinking maybe the trunk channel is a kind of sinuous bodies, but has even larger signal amplitude. Yes, that's what I'm thinking.
Thank you.
Thank you. Then we go to the second promoter, Professor Martinez. Floor is yours.
Waarde promovendus, I'd like to take you up in one of your own pieces of equipment in a drone and ask you to fly around in the Netherlands. You've been living in the Netherlands, you know it's a river-shaped landscape. In these times of climate change, you've been looking at allogenic controls on river patterns and river stratigraphy. What have you learned that you could give the Netherlands, not being a Dutchman, as a piece of advice on what might happen in the Netherlands when we look at climate change and the changes that occur in terms of discharge patterns and sediment delivery and so forth over the coming years?
Promoter. Thank you for your question. Yeah, I think it's very practical to ask what my PhD means to the Dutch people. Yeah, what I'm thinking is, so the Netherlands is mostly alluvial, so it's formed by rivers, but it's very close to the sea level. So it's more in the downstream part. So what we can do is to compare the Dutch territory with our model data in downstream, and also our colleague IQ is working on some protocol data. We can combine it to see.
Thank you, Madam Bido. I request the promovendus to take his seat again. The committee will withdraw for further deliberation in the committee room. This session is adjourned.
The book was there actually.
Oh, really?
Yeah, it was there.
Yeah, this one. Yeah, no, I think normally. I think it's know what happens if this vector. Oh, that's easy. But we want to go back to the version. Oh, that's okay. Great, thank you. Probably I will have some time to clarify my answers.
Youwei, nice. How can I control this stuff also? Yeah, I know.
You know what you should do? You should buy some nicotine sticks. You put it all the way
Just
up.
like you go now. Why is it funny? Sometimes mine, sometimes tough. It's your body.
It was legitimate.
Yeah. Talk to me about ethical engineering, you know?
Then what was the only option? Huh? Was the only option? Our section? Yes. I was the only full professor.
Yeah. No, otherwise you can also ask for full professors from other departments.
Yeah, you have that.
But they don't help, right? They are too far for this.
Oh, yeah.
They ask very general.
Some questions, general questions, specific questions, you know, but how to
Do I do that?
No,
So
yeah.
all
Good quality, everybody's living in but I also that's my case also. Yeah, the people didn't want to use, but solutions for the we are preventing better to go along, so then we can enlarge a bit.
But I didn't hear the people online.
No, me neither.
No? I couldn't hear them perfectly.
Oh, so there are some mics here.
Oh.
But that's what, yeah, also there, you can, better here, so don't worry when you are huh? Don't have to worry when you can hear what they have. Nice.
Honestly, I hope that when I'm defending, it won't be hybrid anymore.
No.
Should be fully online.
Can you imagine?
Can you imagine? Yeah. Like, times that people only get fully online, they just completely empty.
I could still have families, right?
I think at one point there was only the 5 first persons.
Yeah.
But maybe only one, yeah, maybe only one. Up to some number.
And then you were always watching there. And then I saw the camera was watching, was reaching between you and like them and that screen.
So there are,
Yeah, but that's what it is. Live stream.
there are three cameras.
No.
I'm always asking difficult questions. Right?
What would you expect?
I wouldn't. But I think it's not fair that he wants out of us. I don't know why, but
These are the guys that know most of
when you
it.
ask him like an easy question, he says, "Ah, just and if you ask a hard question, he knows all the weakness for us to.
Yeah, but that's
They are just faking.
but that's also why they have left at the end.
I mean, it's just for sure. like I will just talk about that story.
It's good. Well, we don't even get an answer.
No, but that's not.
Yeah.
Only he knew.
Only 12 minutes per 12 minutes, so 4 already, 45. So another 48.
So who took me?
So I
First
use
two
the-
guys.
So the first 4, they have 12. No, so the first 4 people have 12 minutes off, and the last 3 have 5 minutes off. You think we go back? Yeah, thank you.
I reopen the session and request the promovendus to stand in front of the committee. Het College voor Promoties van de Technische Universiteit Delft, vertegenwoordigd door de hier aanwezige commissie, heeft naar kennis te hebben genomen van uw proefschrift met stellingen en naar de verdediging daarvan te hebben gehoord, met inachtneming van de bepaalde in de wet op het hoger onderwijs en wetenschappelijk onderzoek, besloten u de graad te verlenen van dokter. Ik verzoek de promotor door het College voor Promoties als zodanig aangewezen zich wel van de hem opgedragen taak te kwijten.
Uit kracht van de bevoegdheid bij wet toegekend aan het College van Promotie... Ik moet mijn brilletje even opzetten, sorry. Promoties verklaar ik namens dat college, hier vertegenwoordigd door de rector magnificus en de overige leden van de commissie, bij deze u, Youwei, te bevorderen tot dokter en u alle rechten te verlenen welke aan de dokterstitel zijn verbonden. Ten bewijze hiervan overhandig ik u het diploma dat u het recht geeft de titel dokter te voeren.
It's a promoter's privilege to be the first to congratulate the young doctor. Professor Abels, Dr. Abels, the floor is yours.
Thank you. Dear Dr. Wang, dear Youwei, Gong Shi Ni Ge Ni De Jiaren. Don't know if you understood that. And ideal. Congratulations to you and your family. It's of course my great pleasure to speak these words to you. You've done it. You produced a very nice book with lots of data, analysis, and lots of new lines of ideas that we should follow for the years to come. I'm proud to have this book here and keep it in my hands and read it. But above all, now, at this moment, it's not only time to celebrate the book that you produced. Instead, it's particularly also the time to celebrate your personal achievement of writing this book and becoming a lover of science, a philosophiae doctor. Youwei, this is a great achievement that we should celebrate today. Well done, sir. Your sixth proposition sounds Ru Guo Ta Bu Chiao Zan Ni. That's a difficult one, eh? It's Ta Bu Gui Gai Bian Ni. I think you understood.
Yeah, no, I know.
If it does not challenge you, it does not change you. We've not talked about why you added this to your propositions, but I'm pretty sure you've seen some challenges over the past years. And it definitely changed you. The challenges have made you an independent scientist, as we have seen today here in the defense, but have above all made you a stronger person and personality, ready for the life to come and the new life to come. I perfectly remember the day you entered my office and gladly told you were happy to be my first Ph.D. student at Delft. It's also written down back in the book. At Delft we had drawn up lots of ideas based on the previous work we did in the field of astronomical forcing of alluvial stratigraphy. That was going to be your project. And that was also going to be your challenge number one, or maybe I should say your problem number one. We had too many ideas and wanted a lot of different disciplines, as we also have seen today in the defense, a lot of different disciplines to be incorporated in order to answer the questions at stake. You at once had to learn Python and the working of Karstenberg and Bridge modeling, numerical modeling in general, but you also had to learn about cyclostratigraphy and astronomical forcing of climate systems. about fluvial sedimentology in the field and theory, both of coarse clastics and the floodplain finds and soils, and about drone flying, photogrammetry methodology and interpretation software. We wanted you to be a specialist in what we consider ourselves as a rather wide range of specializations. And you did it. And then we do not even talk about that you had to learn the Dutch and Delft culture and life, and the TU Delft as a working place, and about making a living with little money in our expensive country. Later, a lot of other challenges passed by. You lived separate from your beloved ones, your girlfriend in Italy for a long time, your parents and sister in China, and in Corona times this even became worse. And the worst happened when your father turned ill and you couldn't be there with him. It's still a challenge to travel to China, but hopefully it will work out in a few weeks, finally. Corona also meant we missed the 2020 and 21 field campaigns, causing that we could not validate or further investigate some of the great findings that you made, other than inspecting earlier photographs and some photogrammetry models. You worked intensively on this project. You're eager. You always want to learn from others. You read a lot of papers. Sometimes you get so enthusiastic about others' work and other papers that you forget to keep your own track, such that we had to find out which paper you had been reading this time. I also like to refer here to some smaller challenges, such as walking for hours in the Bighorn Basin to very remote sandstone bodies. These sandstone bodies were incorporated in the photogrammetry model, and we wanted the data coverage to be evenly spread over the model. However, clearly the drone had a much more easy pathway to fly to those bodies than you had. And do you remember that we were stopped by the police in China, in icy cold China, during fieldwork because our paperwork was apparently not in order, and you had to bring up your best Chinese acting to get our fieldwork going again. And of course we had challenges that were not difficult to tackle. The Chinese dinners that you prepared in the Bighorn Basin were easy to eat. The lunches we got served in China prepared by the local family, and the very good Chinese food you arranged for lunch here in Delft. Youwei, we had a lot of excellent meetings also, and trips and discussions about science, and even though we did not probably always agree, it was clear that it was always very constructive and very pleasure to have those meetings. It has always been a pleasure and interesting to be discussing science, working life and general life view. And now Youwei, we will clearly miss you in Delft. We will miss you because you've demonstrated to be a very social person as well. You have always helped people, both asked and unasked. You show to think in another's mind, what does he or she need and how can I provide that? The result has been that you have been a very welcome person in our group, in our faculty, and also outside university. This is also because you have shown to approach the life from the positive side. Also in times that your personal life is not feeling like that. Because of private situations, because of deadlines, maybe the deadline of the thesis, it was not always easy. But you still turn on your positive mood every day again to try to make the best out of it. We enjoyed greatly to have you in our team. I'm very happy that you found a great place to continue in science at the University of Virginia in the USA, and I wish you all the best in your future career. But before that, I wish you have a good rest in China, which is well deserved, and have good close contact with your family back there. Youwei, thanks for being with us all these years, and all the best in the near future.
Learned Dr. Wang, you now have the right to use the title of doctor. Your doctorate means that society can rely on your judgment, that you will act transparently and communicate independently about your results and the social relevance of your work. In other words, your doctorate implies that you will uphold scientific integrity. I wish you a great deal of wisdom and prosperity with your new degree. On behalf of the Board for Doctorates of Delft University of Technology, I congratulate you, family and friends, on earning your doctoral degree. Dr. Wang, you may now return to your seat. Ladies and gentlemen, I thank you for your presence. I hereby close this academic session.
Committee members, please stay online. We will make some pictures now with all of you on it. After that, if you want to, you may congratulate our young doctor. Thank you very much. Meneer de rector, gaat u gang.
Well done. Congratulations.
Thank
We
you.
were impressed by a good oral defense, so that's good to hear. I wish you all the best. So I learned that you are going to the United States to continue your work, so that's very good. We have a present for you, and the present is a book you already know. And you have read it, I think, but this is now more valuable because we have added some nice words from the committee members who are here. So I think that is nice. And maybe if you see the other committee members, you can also ask them to write some nice words in it. I wish you all the best for the future, and also today a very nice day.
Okay, thank you.
Thank you very much. Your promoter, Professor Martinius, please.
Youwei, congratulations first of all. I think you did an excellent job. I'm very happy about today and the work that you've produced. And well, we've discussed a lot of things already on the way. You've shown a lot of academic learning and maturity through your work, and I'm very happy about that. You've mastered a lot of topics, and that resulted in an excellent piece of work and an excellent defense. So, congratulations.
Thank you.
Thank you very much. Dr. Abels, do you want to add something?
Of course.
Go ahead, please.
No, it's okay.
Okay, thank you very much. Then we will continue with Professor Fielding from the US. The floor is yours, please.
Youwei, congratulations. Well done. I was very impressed. I think you've made a very good start to your professional life as a scientist, and I hope it continues to be a success. I hope you enjoy the US. I'm sure you will learn even more new techniques and new angles, new approaches, and I wish you all the best in your career.
Thank you very much. Professor Hampson from the UK, please.
Yeah, so Youwei, congratulations again. Well done and very well deserved. You gave a very good defence today, and we asked you about lots of different things, and you gave us good answers, and that's also reflected in what you've written as well. So, yeah, it's great to hear that you've got a chance now to see, friends and family in China again, and also you have an academic position to go to in Virginia as well. That's really good to hear. So, yeah, congratulations, well done, and hopefully we will get a chance to meet in person at some point, either in the US or the UK or Netherlands or anywhere in between. And I guess that also applies to the other committee members as well. So I hope to see you all soon at some point. So yeah, congratulations again, Youwei.
Thank you.
Thank you very much. Professor Kuiper, please.
Yeah, congratulations with your thesis. I was very impressed with your defense today. And what I also particularly liked when I sent you my remarks on the first draft of your thesis, you reported back to me in very much detail. And I actually never had that before, that a PhD student provide me with so much detailed answers. I really liked that. And I wish you all the best in the rest of your career.
Thank you.
Thank you very much. Dr. Stouthamer, please.
Youwei, congratulations. Well, you did an impressive amount of work, and I also really liked our discussion today. It would be nice to continue with that maybe sometime at another moment. And I think you're a very promising young doctor with a strong own opinion, which is good. And well, I wish you all the best and have a good time in the United States.
Thank you.
And
Thank you
a
very
very
much.
nice day today, of course.
Yeah.
Thank you very much. Finally, Professor Bertotti, please.
Hello, Youwei. Well
Hi.
done. Congratulations.
Thanks.
I think you made a really an amazing journey here, and what we discussed also with the other members. I think it's what the growth which you showed in these years is just surprising. At the beginning, you were kind of transparent, like most PhD students, but then meeting you at the coffee machine, I started to notice that you had a smile, and I never knew exactly that smile. It's a bit of a tricky smile, it's kind of cheating me, pulling my leg or a smile. But you were becoming more and more confident. You were putting questions, you're making jokes, and okay, now this is what's going on here. But this turns out to be really a healthy growth of self-confidence and ability to handle questions, to handle things. And this was very, very apparent through the discussion today, where you were in control. Sometimes evading questions, sometimes giving good answers, but you were in control of this growth of self-confidence. I was really privileged to see it, and it's something which you should really be proud of. Well done, congratulations, and good luck.
Thank you very much.
Thank you very much. Dr. Wang, also my congratulations. Maybe you would like to say a few words to your committee members, please.
Okay. So I'm really feel honored to thank you all my committee members. Some of you are strict, some of you are helping in different ways, but I really appreciate all the efforts you have made to improve my thesis. I have really learned a lot. Like Claudia says, I write detailed response back. Also in the meantime, I learned a lot from reading more papers. And so in this way, I'm really learning a lot. And thank you a lot. Then in the meantime, I also want to say thank you to all the audience in this room, and also my family members, my friends, my previous professors behind the screen. So really thank you for your participation. Then almost last, I thank you, my parents, my sister, my parents-in-law, and also my girlfriend, who is going to be my wife soon. Thank you very much.
Thank you very much, Dr. Wang, for your kind words. This will be the end of this defense. Committee members online, if you want to, you may close the lines. Thank you very much.
Thank you.
U bent alle van harte welkom op de receptie, als u wilt.